Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. I also took my Bachelor's of Science at this institution as well in the Pharmaceutical Chemistry program. Today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now I'm just going to get started on our set of questions for today's session. Okay, so question 1 states that the density of aluminum is 2,700 kilogram per meters cubed. How many atoms are in a 2.6 centimeter by 2.6 centimeter cube of aluminum? Okay, so this is a multi-step question. You'll notice that the first thing they give us is the density, which is equal to 2,700 kilograms per meter cubed. They also give us the dimensions of the cube. So the cube dimensions is 2.6 centimeters by 2.6 centimeters. So if we look at the units of the cube dimensions, you'll notice that they are in centimeters, but our density units are in kilograms per meter cubed. So before I do any conversions, I want to first convert my cube dimensions to meters, just so that everything is in the same units. So centimeters to meters makes it 0.026 meters by 0.026 meters. Okay, so like I mentioned earlier, this is a multi-step question. The first step is to find the volume of the cube. Okay, so this is just simple math, I'd say. Finding the volume of a cube is just length times width times height. So since we know the dimensions of the cube, which is the 0.026 meters by 0.026 meters, the volume would just be 0.026 meters cubed. So if we were to multiply this all out, actually maybe I'll just show it if this was the 2.6 centimeters and we didn't convert it. Just to show how you would convert to centimeters to meters from here. So 2.6 centimeter cubed is equal to 17.576 centimeter cubed. So now I'll add another step of converting centimeter cubed to meter cubed. So if you remember the conversion factor for centimeters to meters, there is 0.01 meters in 1 centimeter. And then this whole thing will be cubed. And this gives us a value of 1.758 times 10 to the negative 5 meter cubed. So step 3 is to convert meter cubed to kilograms. So if we recall that our density is 2,700 kilograms per meter cubed, we would just need to multiply our meter cubed value by the density. Okay, so you'll notice that our units for meters cubed will cancel out, and we're left with a value in kilograms, which is 4.75 times 10 to the negative 2. Oh, and this is in kilograms. So now we want to convert kilograms to grams. So 4.75 times 10 to the negative 2 kilograms. And then multiply by the conversion factor to grams. So there are 1,000 grams in 1 kilogram. And you end up getting 47.5. Okay, so step 5 is to find the number of moles. So let's recall that number of moles is equal to mass over molar mass. So the mass is what we found in the previous step, which is 47.5 grams. And the molar mass is the molar mass of aluminum. So if you go to the periodic table, you find it has an atomic mass of 26.982 grams per mole. So if we divide this out, we end up getting number of moles of 1.76 mole. And the last step is to find the number of atoms. So to do this, we just need to multiply our moles by Avogadro's number, which is 6.022 times 10 to the 23. And its units are in atoms per mole. So our moles will cancel out, and we're left with a value of 1.1 times 10 to the 24 atoms. Okay, so like I said, this is a multi-step question, but the more you get used to converting, the faster it'll be to answer a question like this. So the junior tutor said, to answer this, we perform dimensional analysis. First, we can calculate the volume of aluminum. We convert this volume from centimeter cubed to meters cubed. Then we use the density of aluminum to get its mass in kilograms. We convert this mass into grams and kilograms and use the molar mass of aluminum to get the amounts in moles of aluminum. Lastly, we use Avogadro's number to calculate the atoms of aluminum. The solution is shown below. So here they just showed all of these steps in one line. They started off with the finding the volume of the cube, so 2.6 cubed, and then they converted it to meters cubed, then converted it to kilograms, to grams, and then to moles, and then to atoms, and they also got 1.1 times 10 to the 24. So this solution is correct. Okay, so now we can move on to question number 2, which asks, what is the heat of hydrogenation of an organic compound? Okay, so first let's remember what a hydrogenation reaction is. So a hydrogenation reaction is the addition of molecular hydrogen so molecular hydrogen is just H2. And this is added to a double bond. And it reduces the double bond. So I'll just draw out an example. Let's say we had a double bond and we wanted to add H2 . Double bond is reduced. And our two hydrogens can be shown here. Okay, so this is a hydrogenation reaction. The question's asking what is the heat of hydrogenation. And this is the energy needed to perform this reaction. Okay, so let's see what the junior tutor said. The heat of hydrogenation of an alkene is the standard enthalpy of catalytic hydrogenation of an alkene. This means that this is the energy needed to be supplied for the carbon-carbon double bonds to be broken. Yep, so the catalytic hydrogenation of an alkene is always exothermic and will always be negative. Okay, so the solution is correct. Okay, so on to question 3. How do you calculate the electrochemical cell potential E cell with a solved example? So to calculate for E cell, we are going to use the Nernst equation. So this is the potential of the cell. Then I'll just define everything as we go along. Okay, so E cell is the cell potential. And this is in non-standard conditions. E cell, I'll define down here. Okay, so E cell is the difference of standard reduction potential of the cathode with the anode. So it's pretty much the difference between the two. So R is a constant. So its value is around 8.31 joules over mole times Kelvin. T is the temperature in Kelvin. F is another constant, and it's called Faraday's constant. So its value is 96,485 coulombs over mole of the electrons. And finally, N is the number of electrons transferred. Okay, so let's see what the junior tutor said, because I believe they have a solved example. So the galvanic cell is made of 2 electrodes, and its potential is the difference between the reduction potential of the electrodes. The electrochemical cell potential can be calculated using Nernst equation. So in order to find the cell potential at non-standard conditions, we must calculate the electrochemical cell potential at standard conditions. So this is the E cell. It is equal with the difference of standard reduction potential of the cathode with the standard reduction potential of the anode. Yep, so that's what I wrote down here. Standard reduction potentials of the electrodes are constant values, and they are found in appendices. By internation agreement, standard electrode potential measures the tendency for a reduction process to occur at standard conditions. Standard conditions are absolute temperature, which is 298 Kelvin. Molar concentration of the ions in the half cells is 1 mole per decimeter cubed, and pressure of the gases is 101,325 pascals. So they have R as the universal constant of gases, equal to 8.31 joules over mole times Kelvin. T is the absolute temperature in Kelvin, and F is Faraday's number, it expresses the amounts of charges of 1 mole of electrons. Okay, so instead of N, they have Z. So Z is the number of moles electrons that are transferred in the redox reactions. To find that, we must write the overall equation that occurs in the galvanic cell. Q is the quotient equilibrium of the chemical equation that occurs in the cell. Okay, so they have an example here. Calculate the cell potential of a galvanic cell at 300 Kelvin, in which the chemical equation is the following. So they have a chromium ions plus protons plus iodine makes Cr3 plus, iodine, and water. They also give the molar concentrations of all of the different ions. So 2 mole per liter, 1, and 1 times 10 to the negative 5. Okay, so now they have a step-by-step solution. In the first step, we should write the half reactions on both half cells. At the anode occurs oxidation. The element oxidized is iodine because it changes its oxidation number from -1 to 0. So that means its oxidation number increased, so that's how we knew that the iodine is what got oxidized. At the cathode occurs the reduction. Element reduced is chromium because it changes its oxidation number from +6 to +3. So it had a decrease in oxidation number, so that's how they knew that it was getting reduced. So notice that they write the two half reactions from the main chemical equation. So they just took out the iodine, which is what got oxidized, and then this produced the 3 molecules of I2. And then the reason they put 6 electrons on the right side is to balance out the charges. So notice that the iodine has a -1 charge. They needed to add the 6 electrons on the right side to also have a -1 charge. And similarly with the chromium, they have plus the 14 protons plus 6 electrons makes 2 chromium 3 plus 7 H2O. So again, notice that the total charge on the left side is -2 plus -6, which is -8. And then you want to add plus 14. So that's pretty much the same as 14 minus 8, which is 6. So notice our reactants have a +6 charge. And then on the product side, we have 2 chromium 3 plus ions. So our right side is also +6. So we know that the two are balanced in both charges and also with atoms. And they also have the potentials of the cathode and the anode. So I'm assuming this should also be given in the equation as well. And now they have the overall reaction. And then next it says the reactions above can be used to find the number of mole electron Z and also write the expression of the quotient Q. So Z is equal with 6 electrons because that is the number of transferred electrons. Yep. So now they have the expression of Q. So these are quotient values. So they have the notice how they're only using the ions that are involved, and when you have pure substances like solid and liquid, so in this case the iodine and the water, these aren't included in the expression of Q. So it's going to be products over the reactants. So the only product here would be the chromium 3 plus, and the reason it's to the power of 2 is because in our balanced chemical equation there is a coefficient of 2. So that is our only product. Our reactants are the chromium 2 minus ion, the proton to the power of 14, and the iodine to the power of 6. And now they inputted the given concentrations from the question. So the concentration of chromium 3 plus is 1 times 10 to the negative 5. And the concentration of this is 2. Proton is 1. And the iodine is also 1. And they got Q to be equal to 5 times 10 to the negative 11. In the third step, we should calculate the standard cell potential, E cell. So these values were given in the question during this step. So they did 1.33 minus 0.54, and they got 0.79. Okay, so now in the last step, we can calculate the electrolytic potential cell at non-standard conditions using the Nernst equation. Okay, so notice how they have it multiplied by ln Q. Yep, so now they're just plugging in all of the values. And they ended up getting 0.892 volts. Yep, so this solution is correct. So these types of questions are multi-step, and it requires you to really think about how to answer it. It's one of those questions that would be worth maybe like 10 or 12 on a midterm because of how many steps there are. Usually you have to balance your redox reaction, balance your anode and your cathode, and then you have to find the expression of Q and also understand how the Nernst equation works. Okay, so that solution is correct. It's very well detailed. On to question number 4. What was the first subatomic particle discovered? So the first subatomic particle discovered, it was the electron. And it was discovered by J.J. Thomson in 1897. So the junior tutor said J.J. Thomson discovered the first subatomic particle in 1897. Yep, so the solution is correct. The particle, we just add that the subatomic particle was the electron. On to question 5. What is the product of the reaction shown below? So notice we have an aldehyde, and it reacts under basic conditions with heat. So this is an example of an Aldol addition. So notice that there are 2 moles of this phenylacetaldehyde. So it actually reacts with itself in order to form the final product. So I'll draw out the mechanism here. So first I'll draw a molecule of the phenylacetaldehyde. And the first step is the base that that takes this proton, bringing it down. So water was formed when the OH minus took the the hydrogen. And now we have an intermediate that has a negatively charged oxygen and a newly formed double bond right there. So now this is where our second molecule comes in. So the negatively charged oxygen that was formed from our first step comes in and attacks the aldehyde. Which then gives us the following intermediate. And now, lastly, the negatively charged oxygen deprotonates a water molecule to form an alcohol group. Which gives us our final product. Okay, so let's see what the junior tutor said. The reaction has 2 moles of phenylacetaldehyde under basic conditions. The ethanol in the reaction is the solvent, since phenylacetaldehyde is not soluble in water. Overall, the reaction conditions suggest that an aldol addition reaction would occur. The first step of the reaction is the base catalyzed enolate formation. So here they show the base taking one of the hydrogens, forming a double bond, and bringing the electrons up to give the oxygen a negative charge. They also included its a resonance structure as well, showing how the electrons can come back down on itself and give like a negatively charged carbon. Okay, so then enolate addition would occur. This would result in the formation of an alkoxide anion. So here the double bond comes down. All right, let me just notice that mine should also show that this doesn't attack. It should calm down and form a double bond, and it is this that attacks our carbonyl. Yep, so the junior tutor was right. And they got the following intermediate. And then lastly, the negatively charged oxygen comes in, deprotonates a water molecule, and that is how we are left with our final product. Yep, so this solution is correct. It was more correct than mine. And now we can move on to question number 6. Define thermal energy. So thermal energy is the energy contained within a system that is responsible for its temperature. So for example, heat is the flow of thermal energy. Okay, so let's see what the junior tutor said. Thermal energy is the internal energy that a body possesses by virtue of the motion of its particles. It can be considered as the internal kinetic energy of a body. The kinetic energy of the particles that make up a body is found to be related to the temperature. Particles that are moving faster, thus having greater kinetic energy, have a higher temperature than the particles of lower kinetic energy. This suggests that the thermal energy is proportional to the temperature within a given system. Yep, so this solution is correct. Okay, so on to question number 7. What is an integrated law? So this can also be worded as an integrated rate law. So generally speaking, it describes the change in the concentration of reactants and concentration of products. And this is through as a function of time. Okay, so there are 3 main classifications for the different orders of reactions that can be described using an integrated rate law. So I'm just going to make like a summary table. So the 3 different types are a 0 order reaction, second type is a first order, And lastly, you can have a second order. Okay, so first I'll write out the different rate laws that you expect to have when for each different type of order of reaction. So for a zero order, this is when your rate is equal to K. So K is pretty much the slope. And the zero order doesn't depend on the concentration of the element. On the other hand, when you have a first order reaction, the rate is equal to K times concentration. Concentration of, let's say, A. And lastly, when you have a second order rate equation, it'll be rate is equal to K times the concentration squared. Okay, so now I'll show all of the integrated rate laws. So usually these can be derived using like multiple steps. But in the interest of time, I'm just going to write out the integrated rate laws for all of the different orders. For a zero order, okay, so when you have the concentration of your analyte at a given time, so that's what that means by having the T as a subscript, this is equal to negative K of that specific time plus the concentration of your analyte at time 0. So this also means your initial analyte concentration. So that's for zero order reactions. For a first order reaction, it's equal to ln of your concentration of your analyte at a given time is equal to negative K T plus the ln of your initial concentration. Okay, so notice how it's a similar format to our zero order, except now you just have a ln involved as well. And lastly, for our second order, it's 1 over our concentration of analyte at a given time is equal to KT plus 1 over our initial concentration. So again, it follows a similar format, except this time we're looking at the reciprocals of our concentration, and also our KT value isn't negative. Okay, so the last row I'm going to add that might help when you answer the rate law questions is what plot gives a straight line. So for example, if you don't know the order of your reaction, if you were to plot, let's say, the concentration versus time, If this plot were to give a straight line, then we know that we have a zero order reaction. On the other hand, if we have the ln of the concentration versus time, if this gave a straight line, then we know we have a first order reaction. And lastly, if we plot the reciprocal versus time, then we know we have a second order reaction if the plot is linear. So sometimes you'll just have a multi-step question where they give you different concentrations at different times. And then if you plot each of these different things, the plot that gives the straight line is either 0, first, or second. And then from there, by using the integrated rate law, we are able to calculate for K. So let's see what the junior tutor said. An integrated law is an equation that expresses the change in the concentration of reactants and products over as a function of time. The order of a chemical reaction is defined as the sum of the powers of the concentration of the reactants in the rate equation of that particular chemical reaction. Okay. Consider a general reaction with the corresponding rate of reaction. So here they just have a basic reaction, and then this is the general rate of reaction that you would get. The order of the reaction is x plus y, so you can see they just added their exponents. There are three main classifications in order of reactions. A zero-order reaction is the one whose rate is independent of the concentration of the reactant. Half-life reactions are all zero-order of reactions since it does not depend on the initial concentration of the element. The graph for this order of the reaction is a linear relationship between the concentration of the compound and the time. The rate law for such reaction is following. Yep, so now the first order of reaction is where the rate is proportional to the concentration of a single reactant. Reactions that include radioactive decays are all first order reactions. When graphing, this order of the reaction is represented by a linear relationship between time and the natural logarithm of the concentration of the compound. The rate law for such reaction is negative ln kT. Yep. The second order of reaction is a type of chemical reaction that depends on the concentrations of a 1 second order reactant or 2 first order reactions. This order of the reaction is represented by a graph showing a linear relationship between the inverse of the concentration of a reactant versus time. Yep, so this solution is correct. Okay, so moving on to question 8. How do you make an aldehyde from a carboxylic acid? So unfortunately, making an aldehyde from a carboxylic acid doesn't just use one reagent. It's you kind of the certain reagents that you might use to reduce a carboxylic acid would be like lithium aluminum hydride. But however, those reducing agents are too strong and they'll reduce your carboxylic acid straight to an alcohol. So to actually reduce a carboxylic acid to an aldehyde, we're going to add an extra step. So this will take place in 2 steps. The first is to replace the alcohol group with a chlorine. And then the second step is to use the following oxidizing agent. So I'm going to write it in two different ways. So this reagent is called lithium tritert butoxy aluminum hydride. So it can be written like this, or it can be written this. And basically this is what changes our chlorine to the hydrogen to get our final answer. Okay, so let's see what the junior tutor said. We are given some carboxylic acid and are tasked to produce an aldehyde. Recall the oxidation states of organic molecules shown below. So here they show how you can start off with an alkane, and then you can oxidize it to make an alcohol. This can be oxidized to make an aldehyde, which can be oxidized to make a carboxylic acid. And then we can go the reverse direction, carboxylic acid to aldehyde to alcohol to alkane. To get an aldehyde, we must reduce a carboxylic acid. However, carboxylic acids can be reduced using strong reducing agents such as lithium aluminum hydride or LAH. Strong reducing agents will reduce a carboxylic acid 2 steps down, such the final molecule would be an alcohol. Even using stoichiometric amounts will still yield an alcohol. What we need to do is to use a carboxylic acid derivative, which is more reducible than carboxylic acids. These carboxylic acid derivatives are acid halides, esters, and nitriles. The synthesis now would be to first convert the carboxylic acid to any of the derivatives, then perform the reduction. Here we will use acid chlorides. The flow of the synthesis is shown below. Yep, so this is what I used as well, but like the junior tutor mentioned, like you don't need to make an acid chloride. You can use other derivatives such as esters and nitriles, but there are a lot of different ways to do that. So I would say this is one of the more simpler ways to remember. So this solution is correct. Okay, question 9 asks, what do you do in acid-base titration laboratory experiments? Okay, so I'll give a general definition of acid-base titrations. So titrations are used to determine the concentration of A or B by neutralizing so by A or B I mean acid or base. So by neutralizing it with a standard solution of either acid or base, depending on what you're trying to look for. So if you're trying to determine the concentration of an acid, you would neutralize it with a standard solution of base. And if you're trying to determine the concentration of a base, you would neutralize it with a standard solution of an acid. So the standard solution has a known concentration. So during titration reactions, a pH indicator is used to monitor the progress of the titration. Okay, so let's see what the junior tutor said. Titration is a technique to determine the concentration of an unknown solution. In any titration experiments, there are several parts of the titration setup. You have the titrant, which is the solution of known concentration, which is added to another solution whose concentration has to be analyzed. So this is like our standard solution. And the analyte is the solution whose concentration has to be determined. These substances will react, and the reaction is an acid-base reaction which results in salts and water. During titration experiments, the use of indicators is essential because this will tell you the end point of the titration experiment. Indicators are substances that change in color in response to the chemical change caused by the change in the concentration of hydrogen and hydronium ions in the solution, since they change the pH. The common materials and equipment to be used in any titration experiments are the acid, the base, the indicator, burette, the clamp and stand, beakers, flask, and safety goggles. The general steps in performing titration laboratory experiments are... Okay, so here they have a nice diagram showing that you have your titrant that starts at your initial reading, and then you slowly let it react with our analyte of unknown solution. And then once the indicator turns the analyte pink in this example, this is when we would stop adding our titrant. And when we read the volume of titrant that was added, then we can calculate the concentration of our analyte. So they have here a step-by-step solution. Set up the equipment, fill the burette, take the reading before you add anything. Place the flask with the unknown concentration, add indicator. Slowly add the titrant while stirring the flask in a circular motion. Keep adding until visible color change happens, and then take the final reading and then calculate the pH. Yep, so this solution is correct. Okay, so question 10 just asks, how much does 1 gallon of water weigh? Okay, so first let's recall that 1 gallon is equal to 3.785 liters, and 1 liter is equal to 1,000 milliliters. If we say the density of water is 1 gram per milliliter, then we can convert gallons to grams. So for example, let's have 1 gallon, and then using our conversion factor, multiply by 3.785 liters. And then to convert from liters to milliliters, we're going to multiply by 1,000. And then lastly, just to show how to convert to grams, we end up with a final answer of 3,785 grams. Okay, so let's see what the junior tutor said. Weight can mean two things. Weight could either mean how it is used in day-to-day conversation, which is the amount of mass of a substance, or how it is used in physics, where weight is the force exerted on a body by gravity. Let us think about the former. Okay, so they get the gallons to kilograms using conversion factors. Gallon is equal to 3.78 liters. And then they got 3.77743 kilograms. Yep, so which is pretty similar to what I got. That said, we can also consider the second meaning of weight. For this, we multiply the mass of water obtained above to the acceleration due to gravity, which is 9.8 meters over second squared. Okay, so they answered it in 2 ways, but I'll just verify that this solution is correct. And I think we have time for one more question. How many quarts are there in a gallon? So there are, in fact, 4 quarts in 1 gallon. Okay, so the junior tutor said, use the conversion factor 4 quarts over 1 gallon to solve for the number of quarts in 1 gallon. Okay, yeah. Number of quarts is equal to 1 gallon times 4 quarts over 1 gallon, which gives 4 quarts. Yep, so good answer. They also let us know the conversion factor in case we don't just have 1 gallon. We had maybe like 7 or like 6. This would show how you would use conversion factors. So this solution is correct. So that is all the time we have for in today's session. And if you like today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, don't forget to leave a like and a comment if you enjoyed today's video, and share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.